As you can see, we have today, it's a little bit of what we did last time, and then there's two sections that we'll cover, 7.4 and 7.5. And it seems like I'm trying to cram a lot of information here, but those two sections, arc length and surface area, go pretty quick. Then next class, we'll do applications. We are going to start Chapter 8. I normally don't do this. I don't like to start material that's not going to be on a test. But the other option was to give you a test on Thursday. And I didn't want to give you the test on Thursday. But I'll let everyone have the say. Would you like me to finish today surface area and then test you on surface area on Thursday? Or would you rather have new information? Should I even ask you? You'd rather have the weekend? Okay. I think that's probably a good idea. So that's what we'll do. Everyone understand the plan? All right. Let's get back to volumes from last time. And what we basically came up with was that if we had let's say a function and another function, we had them intersecting somewhere, and these were both functions of x. So I can write up here in my blue one, y is some function of x, and then the green one, g, well, here in this case, the y is some other function of x. Then if I want to wrap this around a line, a horizontal line, I have that rectangle. I'll put my arbitrary line. Where should I put it? Doesn't really matter where it is. And I rotate. Then the volume of that solid will be what? And let's make this go from A to B here. Integral A to B. And we also had the pi, right, that we could toss out there. So it's f squared, but it's what I wanted us to see at the end of class last time is don't really look at it as a function, look at it as like a distance. So what I'd like to call it now is this distance right here. Let's just call it the outer, or you call it out or in or something like that. This distance here would be the in. So wouldn't it be the outer distance squared minus the inner distance squared? Okay, so I'm actually going to write that in here. It's the out squared minus in squared, and then dx. Coming up with that out and that in required a little bit of work. And I moved that line above and below the region last time, and it kind of confused things a little, but that's the idea, right? So what we're going to do today is we're going to now take the same concept, but when we're talking about functions that aren't functions of x and not functions of x, but functions of y instead. So these are functions of x because they pass the vertical line test. My rectangle fits in there with the top and bottom being different functions. Yes? Okay, here's where we start new today. Now let's draw a graph. Let's take a green function that does something like this. Let's say a blue one that does something like this. These are not functions of x anymore, right? They fail the vertical line test, but they pass the horizontal line test. So if we turn our heads, we could say they're functions of y. Yes? So I'm going to call the blue one x is some function of y, and the green one I'm going to say is x is some other function of y. So it's the same thing, just switching x's and y's. My rectangle now is no longer vertical, it is horizontal, isn't it? And I want to know what happens when I wrap that around not the x-axis, but around some vertical line instead. So I'm just going to throw an arbitrary vertical line in here. It does not have to be on the right side of the y-axis, right? It could be on the left side, could be the y-axis itself. But the concept's the same. We have two intersection points, right, where the two graphs hit each other. Those are y values, right? And what did we use for y values? C and D instead. So C and D. And when I'm looking here now, I'm going to be looking from my rotation line. This is the dotted line there. There's my rotation line. I'm going to be looking at the distance from that line to the outer function and then inner. I'm not going to say left, right. I'm just going to say out, in, because it's the same thing when we had it rotating the other way. It's just the one that's furthest away from you, the one that's closest to you. So we will have an outer distance and we will have an inner distance. And our integral then should be integral from C to D this time. Pi out front, outer squared minus inner squared dy. So those formulas are almost exactly the same, aren't they? I mean, the only difference is the AB and the dx versus the CD and the dy. With me? Now, what dictates which of the methods you use is usually what line they're asking you to rotate about. Usually, if it's a horizontal line, you're going to be using the other formula. If it's vertical, you use this one. But that's not always the case. So let's just look at an example and work through it. Here we go. So let's take, as this example, y equals 1/4 x squared, x equals 2, y equals 0. Okay, so I'm going to take this region that's bounded by those and rotate it about the y-axis. So the first thing you need is the picture, right? Let's get the picture. So what would this picture look like? And this is where, you might have to use your graphing calculator or whatever method you want. What is x equals 2? Sorry, I'm doing the second one first. X equals 2 is what? Vertical line passing through 2. That's x equals 2. Y equals 0 is what? It's the x-axis, isn't it? Yes. Uh-huh. Without drawing something? Yeah, it might be hard to draw on top of a line, but yeah. You might just thicken it up to show me the region. That's about it. And then 1/4 x squared. 1/4 x squared. Well, that's a parabola, isn't it? And it opens up. So I know it's going to do something like this. And it's going to do something like this. And it's going to hit somewhere over there eventually. Do we see the region bounded by all three? The region in question that we're trying to rotate is this right in here. And we're trying to rotate that around which axis? Y. So here's my y-axis. I'm going to put this in here with the dot, with dashed lines, and then show my rotation along there. Everyone see that picture? But here's where we kind of run into a problem. Because if we're going to rotate around the y-axis, we can't use a vertical rectangle. Okay, with what we've learned, and maybe I should show you this on a new page. If you want to rotate around this, right? If your line is horizontal that you want to rotate around, have you recognized that your rectangle is always perpendicular to that rotation line? So here's our line of rotation. We rotate our rectangle around this way. So if it's the other way, if your line of rotation is vertical, then your rectangle must be horizontal so that they're perpendicular. So when I go back to this right here, if I want to rotate around the y-axis, my rectangle needs to be perpendicular to that, which means that my rectangle needs to be in here like this. Does that make sense? So there's a couple of things we're going to have to figure out. We're going to have to figure out, first of all, where these hit each other, right? So we can get limits on our integral. We're going to have to figure out what the outer and the inner are. Yes? But because we're sideways, we have to have these functions as functions of y instead of x. And the way the problem was presented, that parabola was given to you as a function of x, wasn't it? Y equals 1/4 x squared. We can't use that. We have to solve for x so that it's x equals something in terms of y. Make sense? Okay, so I'm going to go to a new page because I'm going to blow this picture up. Now that I know what I'm working with, I'm going to just do a new drawing. Should we find out where they intersect? Y values, though. See, we need to know where they hit and what that corresponds to with our y values. And down here, that would be 0. And 1. Okay, now I'm going to work it out. But you see, that's what we do need to get, though, right? Those 2 points. So my new page, I'm going to rewrite the stuff I've got here. X is 2. Y is 0. I need to take this and rewrite it as x is some function of y. So how do you solve for x there? Take that, multiply both sides by 4. 4y is x squared. Take square root of both sides. 2 root y equals x. Now I'm supposed to take plus and minus, right? When I take square root. Now I'm only going to take the positive y. Yeah, if you go back to your picture, I'm going to draw it real quick. It's just this top part, right? We just want that part of the parabola. We don't want the other part because that has nothing to do with our region. So the positive answer over here gives us the top part. The negative would give us bottom, but we don't need to have it. Does that make sense? Okay, so that is now my function. I could say f of y equals 2y square root of y. All right, how about my other one? Wasn't that the line x equals 2? So that's already solved, isn't it? I just say g of y equals what? Equals 2. That doesn't change. It's a constant function. So I have my 2 functions, both in terms of y. Now, if I want to know where they hit each other, what do I do? To find their intersection, you set f equal to g to find out when those 2 functions intersect. And the answers you get will be the y coordinates where they hit, not the x coordinates. You see the difference? When we had it before, solved each one for y, we set them equal to each other, we had equations with x. Now that we have them solved for x, when we set them equal to each other, we'll get our y's. So we get 2 root y equals 2. Divide both sides by 2, you get root y equals 1. Square both sides, y equals 1. Right? So the only place that they hit each other is at y is 1. How are we going to know the other one was 0? You have to go to that third equation right here. This one right here. and our picture, right? From our picture, we know it started, turning our head sideways, it started at 0, right? And then it goes up to wherever they hit up there, and that we just determined was 1. Okay? Oh, just plug. Yes, you could determine that either way. But I'm just saying in general, that's what we've been doing. We've been taking our two functions, setting them equal to each other. If it's easy to see and plug in, then it's, but not often will you have x equals 2, All right. No questions?
So I just looked at the one fourth x squared parabola. There's no translation up or down, so it's got to hit the origin.
Mm-hmm.
But can you explain how we would get to that when
Y equals 0 is in our drawing, is the x-axis.
I understand that, but how do you get that one of the intersection points?
It's not an intersection point. See, look, for the parabola is here, right?
Yes.
X equals 2 is here. They only intersect at one point. The other, so that gives you one of your, that's where you stop your integral, right? The thing is, where do you start it?
That's a limit.
That's a limit. So it's you stop at 1, but where do you start? It has nothing to do with the intersection point in this problem. It has to do with that y equals 0 that cuts you off at the bottom. Make sense? Okay. All right, I continue now. Blowing this thing up. This. Here's my rectangle in here. I know that I go up to 1. I know that down here is 0. What is my rotation axis? Sorry. You can't really see the rotation axis, but it's the y-axis. What is my outer distance? What is the distance from here to here? No matter where you put that rectangle, how far away is that top edge? 2, right? That's 2 the whole time. So here comes my integral setting up over here. Integral, here's pi on the outside, go from 0 to 1. The outer is going to be 2, but then squared minus the inner. So what is the distance on the inside here? Always going to be. It's that blue function, right? What is the blue function? Careful. Can't be in terms of x. Has to be in terms of y. So 2 root y. 2 root y. Because remember, this integral has to have dy at the end, right? So it has to be this in terms of y, which is x was equal to 2 root y. See what I'm saying? So this becomes, the inner one is 2 root y squared, then dy. Now you could put all this in a bracket if you wanted to. You don't have to because I understand what you mean, but that's the integral. So you square 2, you get 4, right? You square the other one, you get 4y. So 4 minus 4y. And then antiderivative of 4 is what? 4y. I'll go ahead and take this the rest of the way. So antiderivative is 4y, then minus 2y squared, and then evaluate it from 0 to 1. You plug in 1, what do you get? 4 minus 2, so 2 pi. Plug in 0, what do you get? 0. So the answer is 2 pi.
That's the entire volume shape.
That's the volume. If you took that region and wrapped it around the y-axis, you get that, 2 pi. All right. Pardon me? Yes, units cubed. Yeah, units cubed. Yep, so cubic feet, cubic inches, cubic meters. This is unitless because we don't know what these measurements are to begin with, right? These could be, kilometers. It could be nanometers. Since we don't know our unit of measure, our answer is just a number. If you knew the unit of measure, then you just throw it on as a cubic, unit cubed. All right. Very much the same that we did, what we were doing before, except now we're sideways, I guess. All right. Let me see. I'm trying to find one that's a little more interesting than this. How about... How about y equals e to the negative x squared, y equals 0, x equals negative 1, x equals 1, about the line y equals negative 1. So when I say about y equals negative 1, I mean that's where we're going to rotate it. So the region that we want to rotate is the one that's bounded by those equations. So that's your region. And we want to rotate it about y equals negative 1. So we're going to need to know what e to the negative x squared looks like. Like a bell. Yep. So let me get my graph here. 0 is 1. So at 1, it's like this, right? I'm just drawing the graph here. Looks like is that close enough to what you would get? It's y equal. I just plug 0 in for x into the. Okay, that's e to the negative x squared. Where's x's negative 1? You know what? Let me change. I want to change something in this problem just to make it a little more challenging for us. Let's change our limits. Instead of from negative 1 to 1, let's go from how about 1 to 2? That all right? So y equals 0 is the x-axis again, right? Y equals 0. So I have the x-axis in here. Y equals 0. X equals 1 is a vertical line through 1. And then x equals 2 is a vertical line through 2. Does everyone see the region in question? Where is y equals negative 1? But where are we going to rotate about? Is it vertical or horizontal? It's horizontal, right? So my question to you now is, will you be using an integral with AB and dx or integral CD and dy? AB dx, right? Because your rectangle in here is vertical because your line of rotation is horizontal. Do you know your limits of integration? 1 to 2, right? Do you know Your outer and inner. Yes? Let's try and get the outer. That's the distance from the top all the way to the bottom here, right? Okay, someone help me with that outer distance. So it's the distance from that little guy, right? Looking out. So first from him to the x-axis is how far? 1 plus e to the negative x squared. 1 plus e to the negative x squared. That's our outer. What's our inner distance? What's that? Just 1, right? Because he is 1 unit away from the x-axis, or he's 1 unit away from the bottom function. The bottom function is y equals 0, right? So he's 1 unit away from that, or she. I can't tell if it's a he or she. It doesn't matter. Yes. Pardon me? Oh, yeah, that doesn't matter. We good? What's our integral? Pi, 1 to 2, 1 plus e to the negative x squared, plus 1 squared, which is just 1. Yeah, I don't know why I put plus. Did we put minus on the last one? Okay. So that's your outer squared minus inner squared. This problem, we're not going to integrate that. In fact, you cannot integrate this. There is no way to integrate e to the negative x squared in a closed form. In other words, well, it can't be done, all right? You can do it if you have power series, but we don't have power series yet. So we will attack that integral, this very famous integral right here. There's no technique of integration to do that, but we'll do it later, all right? So this is just a setup problem, nothing more. We're done. Yeah, I got this right out of the book. It just says set up the integral and then use a computer algebra system like Wolfram Alpha to compute the integral. Now, Wolfram Alpha can do it, but it uses power series to do it. What's next? What about... What about y equals, this will be our last example, x squared plus y squared equals 1. Y is greater than or equal to 0. About x equals 6. That is a circle. So remember, these are my equations or inequalities that create my region. Y equals x squared is a parabola. I'm just going to start throwing these out here real quick. I have a parabola. Y equals x squared. I have x squared plus y squared equals 1, which is a circle. Now you can't even put a circle in your calculator in parametric mode unless you solve for y or x. But then you do a square root, you have plus or minus. So you'd have to put in two separate graphs, one to get the top half and one to get the bottom half. But I'm hoping everyone recognizes x squared plus y squared equals r squared is the equation of a circle, radius r. So I have a circle, looks like this. Not bad. X squared plus y squared equals 1. And then y is greater than or equal to 0, which is where? Above the x-axis. So essentially, the last part of this basically eliminates the bottom part here. That comes from the y is greater than or equal to 0, right? So where's the region bounded by those equations and above the or equal to the x-axis? Where is it? Yeah, it's that thing right in the middle, right? This thing in here. I like that acorn shape. See, that's my face. Miley Cyrus, is that what you said? All right, where are we rotating? X equals 6. Where's x equals 6? Where is it? On the right side of it. Isn't it? Somewhere over here. 6. So what do you think about this? Well, the rectangle is supposed to be like this, right? And what's wrong with that? Yeah, see, our rectangle, it touches the top, where it touches on the top and bottom right now, the way I drew it, it's touching the same curve. Right? Y being greater than 0, that just means the region's somewhere above the x-axis. That's what eliminated down here, because if we had below the x-axis, then you could claim that the entire circle is bounded by both, right? Everything in there also. That's a good idea. That's an approach. I like this. You could go and forget this is here right now, right? You could just do this side of it, right? And then the lower one being this, the y-axis. And just do your rectangle from here to here like this. But that would work, and you would go from 0 to where? To where they hit each other. And then you would have to go and use the circle the rest of the way. Do you see that? This is a pain in the ass is what it is. Do you see this? Yes? Understand the difficulty here? It can be done, but it's challenging. Because there's so many different things that have to be done. We have to break it up into different regions. We have to integrate from one spot to the next, then move on. Do y'all kind of see what I'm saying? We would almost have to break this up into like no good. Into like 4 different integrals. It'd be this integral, this one, then this one, then this one. Do you see that? And rotate all of them and then add them up. Vertical, how do you mean? Because it comes from the idea of when we created the washer, right? The washer was the rectangle rotated around, and that created our volume, didn't it? It was pi r squared times dx. Do you remember that? If we turn our rectangle the other way, the formula no longer applies. You get the area, but you don't. We're not trying to find area. We're trying to find the volume, rotating it that way.
Can you find the area as a function of 1 and then rotate it around and change that to function?
Can't. Okay, so here's the reason why I'm showing you this problem. It can be done using what we've learned so far, but it's tedious. Would you agree? Okay, a lot of people skip the next section, 7.3. It's called Volumes by Cylindrical Shells. I'm a huge fan of that section. So I'm going to show you 7.3 and show you that this is going to become trivial. We'll be able to knock this out quick, all right, with 7.3. So I have to develop a whole new kind of idea for us now.
Wait, 7.3 going to be on the test?
Yes. Yep. Well, yes, in the sense that if you're faced with this problem, you're going to have to make a decision of how you're going to do your volume. I would never approach it like this. I would use 7.3. So now we're going to do 7.3. It's called volumes using what are called shells. Now, before we used the washer, didn't we? That was where we had the whole idea came from the idea of this washer. Do I need to remind you? We had two functions that hit each other. We took this little piece, we took it and we wrapped it around, didn't we? Yes? We wrapped it and we got this washer shape. And we have nothing in the middle because it was cut off, right? Okay, and that became the integral a to b. It was the outer one squared minus the inner one squared. I'm going real quick because we've done this. That was where we got the idea of the shell, the washer from. That worked if we could do it where our rectangle was perpendicular to our rotation, right? The problem I just put on the board, we want, like Catherine, like Catherine said, it would be nice if that rectangle was vertical, but then it wouldn't be perpendicular to our axis of rotation. This method in this section, shells, allows you to do vertical and vertical here. So you can have your rectangle parallel to your rotation axis. But we have to create a formula for it first. So here's the way it'll work. Here comes shells. Let's say that I want to take some region bounded by two functions like this. And let's say that I want to wrap it around this axis over here. I can't draw my rectangle horizontal. So let me do this instead. Let me try with a vertical rectangle. Take just that rectangle and wrap it around that dotted line. What would it draw if I wrap it? Like a rubber band, like a cylinder. Do you agree it would look something like this? Yeah. Something like that. Be hollow in the center, right? Hollow in the center. Be wrapped around, almost like a calamari. Right, squid. Sushi, yeah. Just the outside though. Right? Okay, so there you've got it, right? That's what the question would be, what would the volume of that ring be? That shell? Well, let me help you get it, okay? Take some scissors and cut it open. Okay, just come in here and cut that thing open, just lay it out flat. If you do that, you get something like this. Don't you? That's basically a box. Length times width times height. So do you know how high it is? Let's start with height, because that's usually the easiest. It's the upper one minus the lower. That's how tall it is, right? It's the upper minus lower. Now, nope. It's just the top one minus the bottom, right? So I'll say, you want to do up minus upper minus lower. Does that make most sense to you all? The upper one. And in terms of this picture, if we label these F and G, F on top, G on the bottom, it would be F minus G, wouldn't it? F minus G. But I'll stick with upper and lower because we want to generalize this as much as we can. That's how high it is. Okay, can you get me how wide this is? Just this little width right here. That's dx, right? It's that little width of the rectangle, the vertical rectangle. That's dx. So this piece is dx. And the last thing to resolve is how long it is. Well, where did it come from? It's the ring, right? And when we laid it out flat, right? When I take a ring, I cut it and lay it flat, isn't its length the circumference of the circle? And circumference is 2 pi r, isn't it? But what's my radius? Isn't the radius the distance from my axis of rotation to the actual rectangle? I'll call this r for radius. Okay? Now, I'll call this r right here. Go ahead. The volume then of that piece will be, wait, I put r, not r, it's not r, what is it? That's the rate, 2 pi r, I forgot the 2 pi. Jeez, 2 pi r. R is just the radius, now, open it up and now you got your 2 pi r. So the volume should be 2 pi r times upper minus lower times dx. That would be the volume of that one shell wrapped. Well, that's the volume of that one. Now we need to add up an infinite number of them, don't we? And we need the rectangles to start out at the very end, right, at this left end point right here, and then move their way across, right? The rectangles need to move across. So my integral should go from A to B, right? From A to B, move that rectangle across. Y'all follow the development of this? I'm ready for a final formula. It'll be integral A to B. The 2 pi I can pull out. It'll be r. Now r, remember, is the distance from your axis of rotation to your rectangle, right? To your rectangle. And then it'll be the upper one minus the lower one. Dx. That's it. This is called the volumes using cylindrical shells. Here's the way that I think you should remember it. Washers, your rectangle is always perpendicular to your axis of rotation. Shells, they're parallel. Yes?
If we were going to solve for this, do you want us to subtract up and lower than both side r and then do the integral?
It'll depend on the problem. If you can do the subtraction easily, then do it. If not, then you multiply through. Yeah. Let's do an example, all right? Just to see how this works. Let me do you want to try the one we just did? Okay. Let me go back to it then. Here's where we were, right? So looking back at this, if we draw a rectangle in here vertically, we like that because that gives us an upper and a lower function, right? They're pretty obvious. They're not the same. And I can pass through and move left to right, that rectangle left to right, and it'll never change. It'll always be the green one, then the red one. So my upper and lower stay the same the whole time. I like that. Axis of rotation is over there. So let's figure out what our upper and our lower are. Let's figure that out first. Now, they're both going to be functions of what? X or Y? Functions of X, because we're doing vertical. So we need a function of X on top, function of X on bottom. So the green one, how are you going to turn the green one into a function of X? You take this equation for the circle and you solve it for Y. So what would you get if you solve that for Y? Plus or minus square root of 1 minus x squared. Now I'm only going to take the plus because it's only the top part of the circle. Do y'all see that? How about we call that one f of x? Now, how about the bottom one, the red one? Isn't that already solved? Yeah, I'll call that my g of x. So I've got my upper and lower right there, don't I? Now, what? We're going to use that formula, but we also need something else here. What is that? They're intersection points. I need to know where I'm going to start and end my integral. So you have to set them equal to each other. So let's find intersections. So set them equal, you get square root 1 minus x squared equals x squared. To solve that equation, I'll square both sides. I'll move everything over to one side. Yes? Be nice if that factored, huh? It doesn't. So you're actually going to have to solve this using quadratic formula. You would basically make a substitution. You would say u is equal to x squared, then rewrite the problem u squared plus u minus 1 equals 0. I move everything to the other side, yeah. I don't know what these solutions are, and I don't know if I really want to work through this or not. Could you get those answers or not? I mean, this is a, I mean, I hate to say it, but this is a problem that I'm going to give in my 0303 class on their next test. This is a quadratic form equation. This is an equation of quadratic form. You replace your x squareds with u, you get a quadratic, you use quadratic formula, then you switch u back to x squared, and then you solve that. So I would expect you can get that. I would do it, but my calculator's battery died right now, so I can't get these solutions right away. They're going to be ugly numbers, though. But that'll be your limits for A and B. So can I leave it as an open question? The reason why it's not coming out nice is because this problem appeared in the section before the shells. So they're expecting you to do it the other ugly way, and for it to be a challenge. And then they bring in the shells later. All right, you get A and B from this? Negative 3 halves and 1 half? We can try it. Let me plug in negative 3 halves right here. That's 1 minus negative 3 halves squared would be 9 fourths. 5 fourths. Is that right? Did you ever take the square root again? Or? Let's resolve it in a little bit. We'll come back. All right, I want to try and fit my integral in here. Integral, 2 pi's on the outside. Now my A and B, I'm going to leave that as an open question for everyone to go figure out on their own what those solutions were. They definitely intersect, right? Okay, so just a matter of finding them. Now, this is the tricky part. I need to know the radius, which is the distance from my line, right? Distance from my line to my rectangle. Tricky. This is tricky. The distance from my rectangle to my axis of rotation is what?
You just arbitrarily do that rectangle.
That's right. I arbitrarily drew it.
You can put it to where it could be from x equals 0.
That's right, but it moves. It moves. As you integrate from wherever to wherever, you imagine that rectangle's moving. So you can never fix it in one place.
What do you mean, like, if you take, if you do rectangular right at y x equals to 0, at this time,
That distance would be 6, but only when the rectangle's there. The rectangles, there's infinite number of rectangles. We're using the rectangle to just give us a guide as to what one of them looks like, right? We can't ever fix it in one spot. Let me show you. We start here at A, right? And we end at B. So integrating from A to B means start here and start making rectangles, start moving them across, right? As I move across A to B, what variable is changing from here to here? What variable is that? As I move across this way. It's the x value, right? So the x value keeps changing. Over here, maybe I'm at x equals like negative 0.1. And then over here, x is 0.1. Then maybe it's 0.2, right? So x is changing. So isn't the distance from here to my rectangle x? Isn't that distance x? And then the remainder of the distance would be what? In this case, if the distance from here to here is x, then the distance here is 6 minus x. So let's say x was 2. Then the distance would be 4, wouldn't it? So you might be asking yourself, wait a minute, what if you're on this side? It'll be a negative number, so 6 minus a negative would be plus. So you take into account that now you're past 6. It all comes from the picture. You got to be able to draw the picture. You got to understand where things are, how things are moving. So my radius is 6 minus x. And then upper minus lower. So square root 1 minus x squared is my upper, minus the lower is x squared, dx. I'm done. Who has a TI 89 or something? I'm just going to solve that equation. I can't finish this without figuring out what the intersection points are. You got? What's that? Probably. It's all right. I can. It was x to the 4th plus x squared minus 1 negative 0.786. So negative 0.786. Oh, crap. Here you go. This one doesn't do it the way. This one only gives me one of the answers. Okay, you get the other one, all right? Did you? No? Who knows how to use their solve feature on their T89? No one knows how to use their solve feature? No? All of these calculators have a solve feature, but the T89 will give you multiple solutions. So like we're going to have potentially 4 solutions here. So, all right, I'll let you do it algebraically. It's symmetric, isn't it? Oh, it's symmetric. It'll be the same thing. Yeah, that's right. I'm glad you noticed that. It's symmetric, 0.786. Good. Thank you for pointing that out. So that would be your integral. Now, we're not going to evaluate that, all right? We're not going to evaluate that. That would be pretty messy. I see some trig substitution in there, right? 1 minus x squared under a root. That's a trig sub. You might have some integration by parts. So it would be pretty ugly. Yeah. So that's why on the test I say set up. A lot of times on these problems I'll just say set them up. All right, we're going to move on. Man, I don't want to get bogged down in this chapter anymore. Damn it. Let's go to arc length and surface area. Arc length. This is pretty cool, the way you get arc length. It seems like arc length would be easy. You're taking a function that does something like this, and what you want to do is imagine taking it off the piece of paper, straightening it out like a rope, right? Like imagine that was a rope, you take it off the paper, you straighten it out, you lay it down, you measure it, right? That's how long the function is, and it does go from some point A to some point B. So you understand geometrically the idea? What's really cool is you can extend this into three-dimensional space also. So if you have a function that represents, something going through 3D space, you have a way in calculus 3 of taking that path and then pulling it taut and measuring how far it is. It's pretty cool. All right, but for us, we'll stick in 2D. Look at the way we're going to develop this. Unbelievably, it's going to be an integral again, right? It has to be. I'm going to just zoom in. Okay, imagine I'm going to just zoom in on that one little piece right there. I think I'll zoom in down here. On that one little piece, I would have something, I don't know, it might look like that, right? Zoomed in. I just want to take a look at the distance between them. Like, that's obviously not the distance of that little arc, right? But imagine that I'm going to do a smaller piece, and smaller and smaller and smaller. If I basically do an infinite number of these tiny pieces, the smaller I get, the less error I get? Which is the same thing we do with the rectangles. The more rectangles we had, the less error. So let's figure out what this is. Do you agree that this looks like a right triangle? Right? And how wide is this? What's the base of that rectangle? Drum roll. We've been doing this. What have the widths of our rectangles always been? The width, the infinitesimal width, it's been dx, hasn't it? It's still dx. It's how wide that little cut that I'm going to take of the graph is. So it's dx here. What we have not had previous to this was the height. Right? We haven't had the height before. But dx represents the infinitesimal change in x, right? This up and down would represent the infinitesimal change in y. So x changes by an infinitesimal amount, y then changes by an infinitesimal amount. Now, how much it changes by is somehow dictated by the function, which I'll get to. But if I change x, the y has to change a certain way. If it's an x squared function, it might change a certain way. If it's sine, it does something different, right? So once I move a little bit x, how much you move y will depend on the function. Okay. Now, that's the right triangle. Give me the length of the blue. Pythagorean identity. A squared plus b squared equals c squared, right? So this is the square root of dx squared plus dy squared. You buy that? That's what that length is. Now let me talk about, on the side here, let me just talk about this dy thing. Do you remember back in the day when we were first defining derivatives? We said that the derivative of f, this is Cal 1, we could also look at that as dy dx. I'd like to multiply both sides by dx. So I have a definition of what dy is now. It's the derivative of x dx. F prime of x dx. So now come into this formula here and replace dy with that. So we have square root dx squared plus, in brackets, f prime x dx squared. Y'all still with me? Now, when you square two things that are multiplied, can't I square each one? Like square the f prime and then square the dx? I'm running out of room, but I don't want to go to a new page, so I'm just going to come up here. So this becomes dx squared plus, I'm going to do this like this, f prime of x squared, and then the dx separately squared. Y'all see it? Now, what do both of those terms have in common? A dx squared, right? So factor out a dx squared. And you'll be left with 1 plus the derivative of f squared. And can I take the dx out of the root? If I'm taking the square root of dx squared, that can come out as a what? As a dx, and I'm going to slap it on the back of it. Inside I have 1 plus the derivative of f squared, and then outside the square root is dx. Just show of hands, how many of you actually do follow me here? Yes? Okay. At the end of it, it's just going to be a formula, but I'm curious to know how many of you are actually like understanding how this formula is created. What was the question?
I, for some reason, thought that f prime of x equals dx.
No.
Saying it's dy over.
See, if y equals f of x, then if you take the derivative of both sides with respect to x, then the derivative of the left side is the derivative of y with respect to x. The derivative of the right side is f prime of x. Yeah, so the derivative of f is not dx. All right, that's it right there. Because what do we want to do with that one little blue thing? We want an infinite number of them, which makes them smaller, which makes the approximation become the actual arc length. We want to add them up forever. How do we add them up forever? Integral. We want to go from where to where? A to B. And that's your arc length formula right there in an integral. So we get arc length is the integral from A to B, square root 1 plus the derivative of f squared dx. Now this is the arc length of the function f of x on the interval AB. That's right. So if you want to know how long a function is, right, what you would do is you would take its derivative, you would square it, put it next to a 1, take the square root, integrate that. Now, unfortunately, it's very difficult to get arc lengths using our integration techniques because a lot of times functions that you think would be, oh, that'd be easy to find the length of that. The integral becomes very challenging. And I'll show you an example. We'll set it up, but we probably won't be able to evaluate it. Okay, so you ready for your first example? Okay, example. Well, maybe I should show you one that does work first. No, I'll wait. Find length of f of x equals sine x on 0 pi. That seems pretty reasonable, right? That's just taking the sine function, taking that first arc of sine, trying to pull it off the page, straighten it out, and measure it, right? Seems doable. So what do we need in order to compute the arc length? What are the things we need? The derivative. So a lot of times what we'll do is we'll just write the derivative down. And then we need to square that, right? Which would just be cosine squared x. And now throw it into the integral. So I have integral from where to where? 0 to pi, square root, 1 plus cosine squared x dx. Looks harmless, right? If it was 1 minus cosine squared x, it'd be real easy, right? Because 1 minus cosine squared x would be sine squared x, and square root of sine squared x would be sine x, and we'd be in business. Yes. Yep. This integral is not easy. And so I'm going to leave it as just we set it up. So in any time you run into these problems in Calculus 2 classes, the way that the function is picked is vital in determining whether or not you're going to be able to figure it out. So I can't just throw any example at you. I have to make sure that it's picked properly. So the one I'm going to do is, let me see here. Here's one that should work. Let's find the length of let's try this one. Y equals natural log cosine x on the interval 0 to pi over 3. So y equals f of x, right? So we're going to need to know the derivative. What's the derivative of natural log of cosine x? 1 over cosine x times derivative of cosine, chain rule, negative sine x, which is really just negative tangent x, isn't it? Now let's square it. That's just tangent squared x, isn't it? Now the integral. Integral 0 to pi over 3 of square root 1 plus tangent squared x dx. What is tangent squared x? 1 plus tangent squared x is secant squared x. So this is integral 0 to pi over 3 of secant squared x, but then square root, so it's just secant x. Follow or not? We're all right with that? And don't we have a formula for secant? It's what, natural log secant x plus tangent x or something like that? It's natural log secant x plus tangent x. It is, right? Yes? Okay. And then we evaluate that from where? 0 to pi over 3. I'm going to leave the rest to you. But do you understand the setup of that? You see how it had to be perfect? I mean, for it to all work out, everything just had to be great. Yes, I would make it where it would work.
Set it up and solve for credit.
For this one, or I'll tell you which ones you take home and solve. All right, here we go. We need to do another one. So far, it looks maybe like it's a little too easy. So let me try something else. Y equals x cubed over 3 plus 1 over 4x. And you want to do it on the interval 1, 2. So find the arc length. So we'll need the derivative. Now, some books, instead of writing f prime of x, they'll just do this, y prime. That's the same thing, right? So they say y prime is, in this case, what? X squared, that's the derivative of x cubed over 3. And then minus, remember this right here is 1/4 x to the negative 1. All right, bring that x up. It's x to the negative 1. Now take your derivative, negative 1/4 x to the negative 2. Right? Yes, because I'm taking the derivative of this. 1 over 4x is the same as 1/4 x to the negative 1. Now take derivative. Negative 1 comes out. 1/4 x to the negative 2. Rewrite that. Bring the x to the negative 2 back down. Uh-oh. Now what? I have to square it, which means I have to take it and multiply it times itself. Would someone mind shutting that door, please? This is the time where classes switch, I guess. When you expand this out, you should get x to the 4th minus, I'll go a little slower, minus 1/4 minus 1/4 plus 1 over 16x to the 4th. So that's just foiling, right? Do y'all buy that? Which is x to the 4th minus 1/2 plus 1 over 16x to the 4th. So that's your derivative squared. Anyone have a question? All right, integral time. I'm going integral from, what did I say, 1 to 2? Where was it? Yeah, 1 to 2. Square root of 1 plus the derivative squared, so plus x to the 4th minus 1/2 plus 1 over 16x to the 4th dx. Now that integral looks pretty nasty, doesn't it? Doesn't that look pretty bad? But this problem came right out of the book. So I want to show you the algebra involved to take this the whole way. This is why they included it. So first thing I'm going to do is I'm going to take the 1 and the 1/2 and subtract to get 1/2. And I think just for the time being, I'll work with the integral the whole time. I was going to do some scratch work on the side, but I'll just carry it the whole time. I have 1/2 plus x to the 4th plus 1/16 x to the 4th. So all I did there was took the 1 and subtracted 1/2, right? Now what I'm going to do is get a common denominator with everything inside. So my denominators are 2, 1, and 16 x to the 4th. What would my LCD be? You don't need 32. You can just use 16, right? Because 16 is already a multiple of 2. So 16x to the 4th. So make each of those fractions have a 16x to the 4th in the denominator, which means you'd have to make it look like this. Square root of, let me see, I would need an 8x to the 4th on top here. And then on the same thing on the bottom. What would I need on this one, the second one? So that would turn into 16x to the 8th over 16x to the 4th plus 1/16x to the 4th dx. So I just got common denominators between all the terms, right? Put them all together now. I'm going to continue my work here. Square root. I have in the numerator, it's all those numerators together, right? But I'm going to put them in descending order. 16x to the 8th plus 8x to the 4th plus 1 all over 16x to the 4th. Yeah? Remember, I said that they pick these problems very, very carefully so that they work. Do you recognize the numerator? As being something that can be factored as a perfect square trinomial? 16x to the 8th plus 8x to the 4th plus 1. Isn't that 4x to the 4th plus 1 times 4x to the 4th plus 1? Isn't it? FOIL out what I just put there and you get back what's up top. And on the bottom you have 16x to the 4th dx dx. Integral 1 to 2, square root of, the top's just 4x to the 4th plus 1 squared then, and on the bottom, 16x to the 4th dx. Now, I can do the square root of top and bottom separately now. What's the square root of the top? It kills off the squared, so we just get 4x to the 4th plus 1. What's the square root of the bottom? 4x squared dx. No more square root. Everything's good. Life's good. I can take that and split it into two separate fractions, right? 4x to the 4th over 4x squared would become x squared, and the other one would be 1 over 4x squared. Those are all just powers of x. You use power rule, you're pretty much there. So, dot, dot, dot. That is something I would expect you to be able to do. Because it's very common. This is a very common problem. You start with your derivative, you square it, you plug it in, and then the algebra involved to get it to come out clean. I would say my hint to you on these would just be, remember, be looking for that perfect square trinomial to pop out, because that's the only way it's going to work, is if that pops out. Because then you get this, which gives you this. That means you can square root it. All right, that's it for arc length. I should mention also, I'm not going to cover it, but you could have a function. What the heck? You could have a function that does this, where it's not a function of x now, and you want to do arc length. So we would basically turn our heads and we would do it the same sort of way. I'm not going to test you on that. I'm not going to give you any homework like that. But it's an extension just like we've been extending everything sideways, same sort of thing. All right? The integral would just be integral c to d square root 1 plus what? F prime y squared dy instead. But like I said, not going to test you on that. Pardon me? Yes, x prime. So x prime would be f prime y. Y'all just want to have that test on Thursday, or no? All right. Now, check this out. Let's go back to the function. Let's do this guy again. Okay, just one function. We now can do several things with a function like this, right? If someone gives us f, going back to the beginning, we can find the area underneath it, right? That was the first section in this chapter. Find the area below it. We can revolve it around the x-axis. We can revolve it around any horizontal line. Can we revolve that around, when I say that, I mean, can we revolve that around a vertical line? Yes, using the shells, we can do that also, right? Can we find the length of that arc, of that curve? Well, we have a formula for it, right? Can we do it? That's a different question. Now, the last question that we're going to ask about this is if we rotate this around, we know how to get a volume, right? But instead, what would the surface area of that be? So wrap it around. Imagine rotating around the x-axis, and you would get something that looks like this. Right? But forget the volume. Imagine I came in here with a paintbrush and wanted to paint the outside of it. What would that be? Right? So here's how I'm going to do it. I'm going to take a blow up of a little piece again. And that's going to have some little arc, right? Some little arc to it. Which we just did the same exact thing, and we connected it with the line, and we said, okay, that line represented the length, right? Let's wrap, that's supposed to be a straight line. Let's wrap that one little arc around the x-axis. What would we get if we wrapped that little black arc and our blue little line around the x-axis? What would we get? It would look like, I don't know, something like this, right? Ooh. It'd be something like that, wrapped around. Agreed? And I want to know the area of that rubber band. So cut it open, right? Cut it open, lay it out flat. How long is it? What's its length? What's its length? It's 2 pi times the radius of this thing. But how tall was that? How high is the radius? What's the distance from the rotation? Yep, up to this edge. That's the function, isn't it? That's the function. That's our radius. So this length is 2 pi times the function. I just want area. How wide is it? Careful. 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 That's the arc length, isn't it? See, what I did is I took that cut and I wrapped it around. So that width of that ribbon is not dx, it's the arc length. That's the width of that ribbon. Because look, dx is just the width of this width, right? But if up on the curve does something weird up here, right? That there's some curve to it, then that's not dx anymore. That's the arc length of the function on that little infinitesimal piece. So this side of it is actually the square root of 1 plus the derivative of the function squared dx. Sorry, that's real sloppy, but it's the same formula we just did. But now, in addition to it, I'm going to throw what in front of it? 2 pi f of x. Because what I want to do is take that ribbon and add them all up. So the formula will become, for surface area, is going to be integral from a to b. Now I'm going to just throw this out here. 1 plus the derivative of the function squared dx. But in front of it, 2 pi f of x. Now the 2 pi can come out, and f of x has to go in. That's your radius. It's the function's value. That's it. So the only difference between arc length and surface area is 2 pi, and the function has to be thrown out in front of that square root. That'll give you arc length. Now watch this. I mean, that won't give you arc. That'll give you surface area. So I'm going to run out of time, but that's okay. Find the surface area of f of x equals sine x on 0 pi. Now, we just tried this problem a minute ago, and we tried to get the arc length, didn't we? And we couldn't get it. It was a little bit too hard. The integral was a little too hard. So maybe we can get the surface area. You would think, nah, if I can't get arc length, I can't get surface area, right? So this is what it looks like. I'm going to go integral from where to where? 0 to pi. What's on the outside of the integral? 2 pi. And then the function itself, right? Sine x times the square root of 1 plus all that stuff. But we did that already, didn't we? And it was 1 plus cosine squared x, wasn't it? So I'm not going to redo the work for it. Can we do that integral? Yes. This is a basic substitution. Oop. Wait a minute. Basic substitution. U is what? Cosine x. What's the derivative of cosine x? Negative sine x, right? Which is sitting out in front. So I'm going to set up this integral without my limits of integration. I'm just going to set up the integral and then do my work on it. I make my substitution. U is cosine x. Du is negative sine x dx. Minus du equals sine x dx. So now I have my match. Sine x dx is right there. And my cosine x inside here is here. So what would this integral turn into? Okay, integral, how about the negative? Can I pull that outside? Square root of 1 plus u squared du. do we have a formula in the back for square root of 1 or a squared plus u squared? Please, I hope we do. If not, it's going to be a trig sub. Which formula is it? Let me see. Which number? Nope, it's on the That's on the bottom. Square root. There we go. 21? Yes, 21. Oh my gosh. Can I see that real quick? Y'all see formula 21? It's a monster. Number 21. It's you see it there? Square root of a squared plus u squared is u over 2 square root a squared plus u squared plus a squared over 2 natural log of u plus square root of a squared plus, you see that? Plus c. Yeah, but it's there, right? So for us, we can just go straight to this. This is going to be negative u over what? 2 square root of 1 plus u squared plus a squared for us is, all right. I need to put that negative out in front of everything, so I'm going to put a bracket here. A is 1, so 1 over 2 natural log u plus square root 1 plus u squared plus c. Yeah, I need to still go back up to the 2 pi and everything. And I need to switch all my u's back to what? Cosine x's. So this is negative, let's see, cosine x over 2 square root of 1 plus cosine x squared plus 1/2 natural log cosine x plus square root of 1 plus cosine squared x. And then you've got to plug in your, what is it, pi and 0. And you see, though, it works out, though. I mean, at this point, we got to take this back up here, attach the 2 pi to it, plug in. It's going to be a real ugly number, but the point of it is that it can be done. And just by having that sine x out front made this integral possible. When the sine's not out there, can't do it. Okay, here's your formula sheet. We can. It's just a trig sub. Just do trig sub. All those formulas on that sheet are with all the square roots are all just trig subs. They just do them in general. Yeah, I've done them all. At some point, I've done them just for fun, but it's been a while. All right. So what's your feeling on this? I mean, what do you think about all this? Well, it just seems like I feel like
The next test, we're going over trig substitutions now.
yeah, pretty much you got all your techniques of integration all the way up to this. It's going to be a lot, but the test is not going to be any more than maybe 8 questions. I mean, I've got to keep it short, so this is going to be a weird test. There's a lot of information to study. But there's problems that I can give you, like a volume problem where you have to do integration by parts or trig sub or something like that. I can incorporate it into the problem. All right. Well, Thursday we're going to do applications like in physics and engineering type things, and then we're going to move on to chapter 8. We're going to. I mean, that won't be on the test. That won't be on the test. I don't know if I'm going to do hydrostatic pressure or if I'm going to do moments, center of mass. I don't really know yet. Yeah. So as far as homework is concerned, You're going to have to give me, an hour or so to go back to my office. And now that I know what we covered, I got to make sure I pick the problems correctly. I'll send you an email with homework assignments. As far as a review for the exam, you just need to be looking at your homework. I mean, you just got to go back and revisit everything. And
Here's a hell of a lot of material.
all right, have a good day.